Welcome! In this video, we'll be tackling LeetCode problem number 508, titled Most Frequent Subtree Sum. This problem focuses on working with binary trees, and we'll explore how to calculate subtree sums and identify the most frequent ones. Let's dive in. In this problem, we are working with binary trees. A subtree is defined as any node in the tree along with all of its descendants. The subtree sum is simply the sum of all the node values within that subtree. Your task is to find the subtree sums that occur most frequently throughout the entire tree. If there is a tie between multiple sums, you can return all of them in any order. The input to this problem is the root of the binary tree, where each node contains an integer value. The output should be an array of integers representing the most frequent subtree sums. If there are ties, include all the tied sums in any order. This gives us a clear goal to identify the most common subtree sums by analyzing the structure and values in the tree. Let's look at an example to better understand the problem. Consider a binary tree represented by the input array 5, 2, minus 3. If we visualize this tree, it has a root node with the value 5 and two child nodes, 2 on the left and minus 3 on the right. To calculate the subtree sums, we analyze each node and its descendants. For the node with value 2, the subtree is just the node itself, so the sum is 2. Similarly, for the node with value minus 3, the subtree sum is minus 3. Finally, for the root node with value 5, the subtree includes all three nodes, so the sum is 5 plus 2 plus minus 3, which equals 4. Now, let's calculate the frequency of these subtree sums. The sum 2 occurs once, the sum minus 3 occurs once, and the sum 4 also occurs once. Since all the sums have the same frequency of 1, we include all of them in the output. Therefore, the result for this example is 2 minus 3, 4. We can return these values in any order since there are no restrictions on the sequence. This demonstrates how we compute and aggregate the subtree sums across the tree. Here's another example to further clarify. Imagine a binary tree represented by the input array 5, 2, minus 5. In this tree, the root node has a value of 5, with child nodes 2 on the left and minus 5 on the right. For the subtree rooted at node 2, the sum is just 2. For the subtree rooted at node minus 5, the sum is minus 5. For the root node, the subtree sum is 5 plus 2 plus minus 5, which simplifies to 2. Now, let's calculate the frequency. The sum 2 appears twice, while the sum minus 5 appears once. Since 2 is the most frequent sum, it becomes our output, so the result is 2. To complete the problem statement, let's examine some edge cases. For a tree with only one node, like root equals 1, the only subtree sum is the value of that node, so the output is 1. In cases where all nodes have the same value, like root equals 1, 1, 1, 1, the subtree sums will depend on how the tree is structured. For example, sums such as 1, 2, 3, or 4 could appear based on frequency ties. Lastly, negative values must also be considered. For example, if the tree is root equals -1, -2, -3, negative subtree sums will be valid, and the output will include the most frequent sums, even if they are negative. These constraints and edge cases ensure the solution is robust and works for a variety of input scenarios. To solve the problem of finding the most frequent subtree sum, one approach we can consider is the brute force method. The intuition here is to calculate the sum of all subtrees in the binary tree. For each node, we recursively compute the sums of its left and right subtrees, then add the node's value to get its subtree sum. These sums are stored in a hash map to track their frequencies. Finally, we go through the hash map to identify the sums that occur most frequently. However, there are important observations to make about this approach. Each subtree sum is composed of the sums from its left and right subtrees, along with the node's value. This means that when subtrees overlap, their sums are recalculated multiple times, which leads to inefficiency. The time complexity can be as bad as O(n) squared, in the worst case due to these redundant calculations, and we also need O(n) space for the hash map. While this method is straightforward to implement, it is computationally expensive, especially for larger trees, because it does not optimize for overlapping subproblems. Instead of the brute force approach, we can use an optimized method that relies on post-order traversal combined with memoization. This approach calculates subtree sums in a single traversal of the binary tree. Here's how it works. As we traverse the tree, for each node, we compute the sum of its left subtree, its right subtree, and its own value. The sum is then recorded in a hash map, where the key is the subtree sum and the value is the frequency of that sum. Once the traversal is complete, we can iterate through the hash map to determine the sums with the maximum frequency. The efficiency of this approach lies in some key observations. Post-order traversal processes the tree from the leaves upward, ensuring that each subtree sum is computed only once. By using a hash map, we can track and query frequencies in constant time for each operation. This method reduces the time complexity to O(n), as we only traverse the tree once, and the space complexity remains O(n), due to the hash map and recursion stack. While it may be slightly more complex to implement compared to the brute force method, the optimized approach is far more efficient and well suited for larger trees. The strategy we ultimately choose is the optimized approach using post-order traversal with memoization. This method is preferred for several reasons. First, it eliminates redundant calculations by leveraging the nature of post-order traversal, which ensures that all subtree sums are computed only once. Second, it utilizes a hash map to efficiently record and access frequencies, making these operations extremely fast. Finally, it is highly scalable, with a linear time complexity that makes it practical for handling large input sizes. When comparing this method to the brute force approach, the differences are clear. While the brute force method is easier to understand, it suffers from inefficiency due to repeated calculations. On the other hand, the optimized approach is slightly more complex to implement but computes all subtree sums in a single traversal, making it much more efficient. The key insight here is recognizing that the brute force approach repeatedly recalculates overlapping subtree sums. By using post-order traversal, we avoid these redundant calculations entirely, leading to significant performance improvements. This realization was the turning point in identifying the most effective strategy for solving this problem. While the optimized approach is clearly superior in terms of efficiency, it does come with certain trade-offs. Implementing memoization along with the traversal logic requires careful handling of recursion. This added complexity means that the implementation may take slightly more effort to get right, particularly for those less familiar with recursive tree traversals. However, the benefits far outweigh this drawback. The significant gains in efficiency, especially for larger trees, make this approach the better choice for the problem. By balancing the slight increase in implementation complexity with its performance advantages, post-order traversal with memoization emerges as the optimal strategy for finding the most frequent subtree sum. To solve this problem, we need to calculate the subtree sums for all subtrees in a binary tree and determine how frequently each sum occurs. A subtree sum is defined as the total sum of all node values within a subtree rooted at a specific node. The input is a binary tree, where each node has an integer value and pointers to its left and right child nodes. The key idea here is to compute these subtree sums recursively for every node and use a hash map to track the frequency of each unique sum. This hash map will allow us to efficiently record and access how often each sum appears. The algorithm centers around a recursive helper function called compute_subtree_sum node. This function takes a node as input and calculates the sum of the subtree rooted at that node. If the node is none, the base case returns 0, as it contributes nothing to the sum. For non-null nodes, we compute the sums of the left and right subtrees by making recursive calls to compute_subtree_sum. Adding these results to the node's value gives the current subtree sum. This sum is then added to the hash map, where we increment its frequency. Finally, the function returns the current subtree sum to its parent node. The main function initializes the hash map and invokes the recursive helper function starting at the root node of the tree. Once all nodes are processed, the results can be extracted and analyzed from the hash map, such as finding the most frequent subtree sum. Recursion is a natural fit for this problem because binary trees are inherently recursive structures. Each subtree can be treated as a smaller instance of the problem, and recursion allows us to neatly compute the solution for each subtree. Using a hash map is crucial for efficiency, as it lets us insert and look up subtree sums in constant time. Without the hash map, counting frequencies would require additional nested loops, which would significantly increase the complexity of the solution. Additionally, the use of post-order traversal ensures that we compute the subtree sums for a node's children before calculating the sum for the parent node. This traversal order avoids redundant calculations and guarantees that we build the sums in a bottom-up manner. This algorithm relies on two main data structures. First, the binary tree itself, where each node is represented as an object with a value and pointers to its left and right children. Second, the hash map, or frequency_map, where the keys are the subtree sums and the values are their corresponding frequencies. The hash map is essential for efficiently tracking and retrieving the frequency of each unique sum. Together, these structures enable us to compute subtree sums recursively, record their occurrences, and extract meaningful insights about the tree. The key operations in this algorithm determine its overall complexity. Each node in the tree is visited exactly once during the traversal, resulting in a time complexity of O(n), where n is the number of nodes in the tree. Operations on the hash map, such as insertions and lookups, have an average time complexity of O(1). For space complexity, we require O(h) space for the recursion stack, where h is the height of the tree. Additionally, the space required for the hash map depends on the number of unique subtree sums. In the worst case, where all nodes have distinct sums, this would also be O(n). Finally, it's important to consider edge cases. If the tree is empty, meaning the input root is none, the algorithm should return an empty frequency map or an equivalent result. For a tree with a single node, the subtree sum is simply the value of that node. When there are duplicate values in the tree, it's possible for different subtrees to produce identical sums. The hash map handles this scenario by correctly tracking the frequency of each unique sum, regardless of how it is generated. These considerations ensure the algorithm is robust and handles all possible inputs effectively. Here, we start by importing the default dict from Python's collections module, which will help us efficiently track the frequency of subtree sums. Then, we define the treeNode class to represent the structure of a binary tree node. Each node contains a value and optional left and right children. Next, we introduce the solution class, which contains the method findFrequentTreeSum to solve the problem. Inside this method, the first thing we do is handle the edge case where the root is none, returning an empty list since there are no subtree sums. Now, we define a nested helper function, calculate_subtree_sums, which will recursively compute the sum of all nodes in a subtree. If the current node is none, meaning we've reached a leaf, we simply return 0 as the sum. For non-null nodes, we calculate the sums for the left and right subtrees by making recursive calls to this function. After obtaining the left and right subtree sums, we compute the sum for the current node by adding its value to the sum of its left and right subtrees. This value represents the total sum of the subtree rooted at the current node. Finally, we update the sum_frequency dictionary to increment the count for this subtree sum, effectively tracking how often each sum appears. The helper function then returns the computed subtree sum to its caller, allowing the recursion to propagate these values upward. Moving on, we initialize the sum_frequency dictionary using defaultdict, int, to store the frequency of each subtree sum as we compute them. With the setup complete, we call calculate_subtree_sums on the root node to start the recursive computation of all subtree sums in the tree. Once all the subtree sums have been processed, we determine the maximum frequency by finding the highest value in the sum_frequency dictionary. This tells us how often the most common subtree sum appears. Using this maximum frequency, we then collect all subtree sums that occur with this frequency. We accomplish this with a list comprehension that iterates over the keys in sum_frequency and selects only those sums whose frequency equals the maximum. Finally, we return this list of most frequent subtree sums as the result of the function. Here, we start by defining the treeNode class, which represents a node in the binary tree. Each node contains an integer value, a reference to its left child, and a reference to its right child. The constructors allow us to initialize nodes in different ways, either with just a value or with both a value and child nodes. Next, in the solution class, we define the main method findFrequentTreeSum to solve the problem. First, we handle the edge case where the root of the tree is null by returning an empty array. Then, we declare a hash map called sumFrequency, which will help us store the frequencies of the subtree sums as we calculate them. Finally, we prepare to compute these sums recursively by calling a helper method that we will build shortly. We now call the helper method calculate subtree sums to compute the subtree sums for the entire tree and populate the sum frequency map. Once we have all the subtree sums and their frequencies, we determine the highest frequency using collections.max on the values of the map. This gives us the maximum occurrence of any subtree sum. With this maximum frequency, we then iterate over the entries of the map to collect all subtree sums that match this frequency. These sums are added to a result list. Finally, we convert this list into an integer array using JavaStreams and return it as the answer. This ensures our output is in the desired format, containing all the most frequent subtree sums. The calculate subtree sums method is a recursive function that computes the sum of all nodes in a subtree rooted at the given node. If the current node is null, we return 0, as there is no contribution to the sum. Otherwise, we recursively calculate the subtree sums for the left and right children of the node. Once we have these sums, we compute the total subtree sum for the current node by adding its value to the left and right sums. After calculating the subtree sum, we update the sum frequency map by incrementing the frequency of this sum. Finally, we return the subtree sum so that it can be used in the calculation of higher-level nodes. In this example, we are given a tree with 3 nodes, where the root node has a value of 5, and it has 2 children, 2 on the left and -3 on the right. To begin solving, we initialize an empty dictionary called sum_frequency to keep track of how often each subtree sum occurs. Then, we start our recursive calculation at the root node, which has the value 5. The first step is to calculate the sum for the left subtree rooted at node 2. Since node 2 has no children, both its left and right subtree sums are 0. Therefore, the subtree sum for node 2 is computed as 2 plus 0 plus 0, which equals 2. We then update the sum_frequency dictionary to reflect this, setting the count of the subtree sum 2 to 1. Next, we move on to the right subtree rooted at node -3. Similar to node 2, node -3 has no children, so its left and right subtree sums are also 0. The subtree sum for node -3 is calculated as -3 plus 0 plus 0, yielding a sum of -3. We now update the sum_frequency dictionary again, adding the subtree sum -3 with a count of 1. Returning to the root node, we proceed to calculate the sum for the entire tree. The left subtree sum, which we previously calculated, is 2, and the right subtree sum is -3. Adding these to the value of the root node, 5, we compute the subtree sum for the root node as 5 plus 2 plus -3, which equals 4. We then update sum_frequency to include this new sum, resulting in the dictionary 2, 1, -3, 1, 4, 1. Now that we have computed all subtree sums, the next step is to determine the maximum frequency of these sums. Here, the maximum frequency is 1, as each sum appears only once. Finally, we extract all subtree sums that occur with this maximum frequency, which are 2, -3, and 4. The output for this example is therefore the list 2, -3, 4. Moving on, let's consider another example where subtree sums repeat. In this second example, the tree is similar to the previous one, but the right child of the root has a value of -5 instead of -3. We start with an empty sum_frequency dictionary and begin the recursive calculation at the root node, which has the value 5. First, we calculate the sum for the left subtree rooted at node 2. As before, node 2 has no children, so the left and right subtree sums are 0, resulting in a subtree sum of 2 plus 0 plus 0, which equals 2. We update the dictionary to 2, 1. Next, we compute the sum for the right subtree rooted at node -5. Node -5 also has no children, so its left and right subtree sums are 0. The subtree sum for node -5 is therefore -5 plus 0 plus 0, which equals -5. The sum_frequency dictionary is updated again to include this, becoming 2, 1, -5, 1. Finally, we calculate the sum for the entire tree. The left subtree sum is 2, and the right subtree sum is -5. Adding these to the value of the root node, 5, we calculate the subtree sum for the root as 5 plus 2 plus -5, which equals 2. This time, the subtree sum 2 appears again, so we increment its count in the dictionary, updating it to 2, 2, -5, 1. Now that all subtree sums have been calculated, we proceed to find the maximum frequency in the sum_frequency dictionary. Here, the maximum frequency is 2, as the sum 2 occurs twice. We then extract all subtree sums that appear with this frequency. In this case, the only subtree sum with a maximum frequency of 2 is 2 itself. Therefore, the output for this example is 2. Let's now look at a simpler example involving a tree with only a single node. In this final example, we are given a tree with a single node, which has the value 1. As usual, we start by initializing an empty sum_frequency dictionary. Since this tree consists of only one node, the recursive calculation is straightforward. The left and right subtree sums for node 1 are both 0, as it has no children. The subtree sum for node 1 is therefore calculated as 1 plus 0 plus 0, which equals 1. We then update the sum_frequency dictionary to reflect this sum, setting the count of 1 to 1. Next, we find the maximum frequency in the dictionary, which is 1, as the sum 1 appears only once. Finally, we extract all subtree sums with this maximum frequency. In this case, the only subtree sum with a maximum frequency of 1 is 1 itself. The output for this example is 1. To analyze the time complexity of our solution, we start with the traversal of the binary tree. The calculate_subtree_sums function performs a depth-first traversal, visiting each node exactly once. Since a binary tree with n nodes has each node visited once during this traversal, this step contributes O(n) to the overall complexity. Next, consider the frequency dictionary. For every node, we calculate its subtree sum and update the sum_frequency dictionary. Dictionary operations like insert or update are O(1) on average but can degrade to O(n) in the worst case, due to potential hash collisions. However, since we update the dictionary n times, this step is O(n) in the average case. Finally, after processing all nodes, we need to determine the maximum frequency in the dictionary. If there are k unique subtree sums, iterating through the dictionary takes k time. In the worst case, where all subtree sums are unique, k equals n, this step also takes n. The last step in our time complexity analysis is collecting the results. Here, we iterate through the dictionary to gather all subtree sums that have the maximum frequency. This step also takes k time, where k is the number of unique subtree sums. In the worst case, where all subtree sums are unique, this step is n. Combining all these steps, the overall time complexity of the solution is n. This is because the traversal of the tree, which is n, dominates the runtime. Now, moving to space complexity, let's consider the recursive call stack. The depth of recursion depends on the height of the binary tree. For a perfectly balanced binary tree, the height is log n. However, in the worst case of a completely unbalanced tree, the height can be n. This means the space required for the call stack is h, where h is the height of the tree. In addition to the call stack, we also need to consider the frequency dictionary, sum_frequency. The size of this dictionary depends on the number of unique subtree sums. In the best case, where all nodes produce the same subtree sum, the dictionary contains only one entry, so its space usage is 1. On the other hand, in the worst case, where all nodes have unique subtree sums, the dictionary will have n entries, resulting in n space usage. Finally, we have the result list, which stores all subtree sums with the maximum frequency. In the worst case, all n subtree sums could have the same maximum frequency, leading to n space usage for the result list. When we combine these factors, the overall space complexity is n, which is dominated by the dictionary and the result list in the worst case scenario. Comparing this optimized solution to a naive approach highlights its efficiency. In the naive approach, we would compute the subtree sums for every node independently in a bottom-up manner. For each node, this would involve visiting all nodes in its subtree. In the worst case, this would lead to a time complexity of n squared, which is significantly worse than our optimized n solution. The optimized approach avoids redundant computations by using a single post-order traversal to calculate all subtree sums in one pass. By leveraging a dictionary to count frequencies efficiently, we eliminate the overhead present in the naive approach, making the solution far more time efficient. To confirm the big O complexity mathematically, we observe that the post-order traversal ensures each node is visited exactly once, contributing n operations. Dictionary operations such as insert and update are O(1) on average, and iterating through the dictionary takes O(n) in the worst case. Summing these contributions, the total number of operations scales linearly with the number of nodes, confirming the time complexity is O(n). For space complexity, the recursion depth is bounded by the height of the tree, which is O(h). Additionally, the dictionary and result list together require O(n) space in the worst case. Combining these factors, the overall space complexity is also O(n), making this an efficient solution in both dimensions. When working on subtree sum problems, there are several common mistakes to watch out for. First, it's crucial to handle negative values in subtree sums. While many problems assume positive integers, trees can also contain negative values, which, if overlooked, may distort frequency counts and lead to incorrect results. Next, ensuring the base case and recursion is correctly implemented is vital. Forgetting to handle null nodes properly can result in runtime errors, so always return 0 for null nodes when calculating subtree sums. Another frequent issue is double counting nodes. This happens when a node's value is mistakenly added multiple times to its subtree sum. To avoid this, ensure each node contributes to the sum exactly once. Lastly, watch out for inefficient frequency calculations. If you calculate frequencies during each recursive call instead of using a global dictionary, you may end up with redundant computations, which can unnecessarily increase the time complexity of your solution. Now, optimizing for larger trees is another critical consideration. A brute force approach might work for smaller inputs but can exceed time limits for large trees. To address this, aim to calculate sums and frequencies in a single traversal, which significantly improves efficiency. From an interview perspective, it's essential to fully understand the problem scope. Be sure to clarify whether the input tree may include negative values, zeros, or duplicate values, as these factors will influence how you handle edge cases and design your algorithm. Additionally, always discuss time complexity. While the brute force method operates in O(n)², pointing out how a single traversal reduces this to O(n) demonstrates a strong understanding of optimization. Hash maps are particularly helpful for frequency counts, as they reduce redundant calculations and simplify the logic. Finally, don't forget to communicate edge cases clearly. Think about scenarios like trees with all nodes having the same value, single node trees, or those that are deeply unbalanced, as these can reveal how robust your solution is. There are also several related problems worth exploring to deepen your understanding. For instance, LeetCode 508, which we're discussing, focuses on finding the most frequent subtree sum. LeetCode 124, the binary tree maximum path sum, is another great problem that involves recursive calculations. Similarly, LeetCode 543, diameter of binary tree, and LeetCode 437, pathsum 3, are excellent examples of tree-related problems that build on similar concepts. As for alternative approaches, the brute force method is a straightforward starting point but comes with the trade-off of inefficiency for larger trees due to repeated calculations. The optimized single traversal approach is far more efficient, operating in O(n), but it requires careful handling of recursion and the use of hash maps. Lastly, iterative DFS or BFS can help avoid recursion stack overflow in deeply nested trees, though implementing these approaches elegantly can be more complex. Each method has its pros and cons, so choosing the right one depends on the specific constraints and requirements of the problem. Great job! We've summarized the key points of solving the most frequent subtree sum problem. Remember the importance of post-order traversal and hash maps for similar challenges. Thank you for watching, and we'll see you in the next video. Don't forget to like and subscribe. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!